Hi, you are all warmly welcome once again to this series on strength of materials and to this channel. Kindly subscribe, like, share, leave your comments and suggestions as well. Continuing with our series on strength of materials, today we are looking at deformation of bars by Axial Loads. Example 1. Let's look at our example and how to deal with it. Good. The aluminium shaft is subjected to axial load soon. The diameter of each segments are AB equal to 4 inches, BC is equal to 2.5 inches, CD is equal to 1.5 inch. Take modulus of elasticity of aluminium to be 1.9 times 10 to the power 6 KSI. Determine the deformation in AB, BC, and CD, the displacement of NA with respect to C, and C, the displacement of NA with respect to NB. So let's see how to solve this problem. Good. We have our question. This is a diagram we have been given. Let's look at how we are going to evaluate and solve this problem. What you are going to do is that anytime you are given a question on complex axial loads, what you do is that you divide into sections using material properties. Material properties. Which is related to the modulus of elasticity. Number 2, you divide according to forces. So anytime you encounter a new force, you also divide. And number 3, you use area or diameter. So anytime you encounter a new diameter or a new area, you need to also divide. Using 3 criteria, let us look at how we can also divide our structure here. Now, looking at this structure, both the two ends are all free, which means that you can start your analysis from each of the sides. You can start your analysis from each of the sides. So if I decide to start my analysis from A, then you can see that as I'm moving from A, I encounter a change in diameter, so I can divide it into that section. There's also forces there, but we are going to, because we have divided by the diameter, that will be enough. And once we also move from there, you can see that diameter is uniform onto this section where we are encountering a different diameter. So we also divide at that section C. And from section C, you can see that we'll be continuing. There's no change in diameter. We don't encounter any force until the end. So this is also going to be another section. So you have sections 1, 2, and 3. And once you have been able to do that, you draw free body diagram for each of the sections to determine the internal forces within them. So let's take A to B. When we pick A to B, now you can see that from A to B, our structure is going to be like this. A rod, we have 9. This is going this direction, so this is 9. And the internal force in A to B, we can call it T1. And from there, we can say that any force which is going to the left is negative, any force going to the right is positive. So from here, we can say that negative 9 plus T1 should be equal to 0. Then from there, we can say that T1 is equal to 9. Good. Q1 is equal to 9 kips. We can also draw the free body diagram for section 2. When you are drawing section 2, because you are determining the internal forces, all the forces here will affect the internal forces in the section 2. So we draw from the free end up to where the section 2 is ending. And our free body diagram is going to be like this. This is for section B, C. The free body diagram is going to be like this. There's a change in diameter. This is 9 going this direction. We have 3 going this direction. This is also 3 going that direction. And to every action, this is where we are cutting. We are saying that to every action there is equal and opposite reaction, or at the middle, wherever you want to cut. So our internal force in BC, we can call it P2. Once you have been able to do that, we can just write our equilibrium equation. The 9 is going to the left, so we have -9. The 3 is going to the right, plus 3. This 3 is also going to the right, plus 3. This P2 is going to the right, so plus P2 will be equal to 0. Then from there, we can make P2 the subject. From there, you can see that P2 will be equal to 3 kips, because this will be negative, you send to the other side, which will give you 3 kips. Good. Then we go to the third section, section 3 here. Now, because we have none of the ends are restricted, or none of the ends are fixed. For section 3, you can decide to cut it this side, and you take your analysis in this direction, or you can decide to just take it from this direction here. And the answer will be the same. You are going to get the same thing at the end. So if we pick from A, we are going to have our structure like this. So we have our 9 going this way. We have a change in diameter here. Then we have a force of 3 at this side, a force of 3 at that side also. And then we have the new change, another change in diameter here. And there's a force there. Sorry for that. Let me draw it a bit bigger so that we can be able to visualize. From there. So we have a diameter here and another change in diameter at this side. And there is a force here. And that force is 5 kips. So the internal, if we decide to take it from A to that point, then our internal force would be like this. We can call it P3. And from there, we can see that 9 is going to the left, so negative 3 is going to the right. They are all positive. 5 is going to the right, is also positive. Our P3 is going to the right, is also positive. Is equal to 0. Then from here, we can calculate P3 as equal to -2 kips. As -2 kips. Good. You can also decide to take, as I said, you can decide to take it from the right, since we have 2 free ends. So even in that case, if you decide to take the third section from the right, from B up to that point, you are also going to get your free body diagram like this. You have 2 going this way, and the other one will be in the opposite direction. So we can say that this is P3, this is 2. So you can say that P3 going to the right -2 will be equal to 0. And from there, our P3 will be equal to 2 is the same thing, just that their direction, you can see that their direction here is changing. That is why we are getting positive 2 here. The direction of the angles we indicated are changing. That is why we are getting positive. If we were to indicate this direction as going this way, we would have also gotten negative 2 as in this case. There, since this is going that way, the other one should be the opposite direction. So we are going to get the same thing from there. Once you have been able to get the internal forces, the next thing to do is to determine the deformation associated with each of the sections. The deformation with each of the sections. Deformation in each of the various sections. That is what we are going to do now to calculate the deformation in each of the sections. So first of all, let's take the deformation in AB. For AB, AB is a section 1 from point A to point B. So we said that the deformation in AB is going to be, the question says that we should determine the deformation in each of the various sections. Therefore, deformation in AB, you can see that delta AB should be equal to the force, the internal force, which is P1, times the length L1 over A1 times the modulus of elasticity. You can call it P1. So from here, our deformation at B should be equal to the force P1 is 9 kips, which is 9 times 10 to the power 3, times the length of that. So from this point, the section is from this point to that point. Therefore, the length is 5 inches all over the area. Because it's a cylindrical, area is going to be pi d square on 4 or pi r square. Which of them is easier for you? You can just choose. So we are going to get pi is 3.142 times the diameter of that section. The question we answer that the diameter of that side is 4. So you have 4 squared over 4 times the modulus of elasticity, which we are told that it is 1.9 times 10 to the power 6. Or it is 1.9 million or something. So we can say that that one is 1, but it was given in kips or KSI. It was given in KSI. So anytime you are given in KSI, what you do is that you are going to multiply by another times 10 to the power 3. Don't forget that one. Anytime you are given in KSI, also add times 10 to the power 3, which will give us 6 plus 3, and that will be equal to 9. So from there, the deformation of AB should be equal to 1.696 times 10 to the power -5 inches. So that is a deformation in A. You can as well determine the deformation in B to C. Deformation in B to C, our delta will be equal to P2. In that case, we are dealing with P2 L2 over A2 and E2. So from there, the deformation in BC is going to be the force in P2. We are told that it is 3 kips, so 3 times 10 to the power 3 because of the kips times the length of the section. The length of the section, don't add this 45. It is only from B to C. The section is only from B to C. So the length of the section is going to be 90 over our area, which is 3.142 times the diameter of the second section. The diameter there is 2.5. We have 2.5 square all on 4 times our modulus of elasticity, which is 1.9 times 10 to the power 6. Don't forget that it was given in ASI. We said that you multiply by another times 10 to the power 3. And from there, our deformation for section B is equal to 2.895 times 10 to the power -5 meters. And we can calculate the deformation in the last side, which is from C to D. From C to D. So from C to D, the deformation is going to be BCD will be P3, P3 L3 over A2, A2, A3, E3, and that will be equal to, we know that the deformation in the third section is -2, so we have the -2 pips, -2 pips, which is -2 times 10 to the power 3 times the area, the length of the section. B, C to D is 50. Don't add the others. So times 50 over our area 3.142. 142 times the diameter, which is 1.5 for that side, 1.5 all over 4 times our modulus of elasticity, which we are is the same as the ones we have used, the 1.9 times 10 to the power 9, which is 6 plus 3. And from there, our deformation for that section is going to be -2.978 times 10 times 10 to the power -5. So we are done determining the deformation in each of the sections, but it doesn't end there. Don't forget that in the question, the second part of the question asks us to find the displacement of point C. The displacement of point C. The displacement of point C. Displacement of point C as a result of. So the displacement of point C here with respect to A, point C with respect to A, how C is going to deflect when you are starting from A means that C is going to deflect if you are starting from the point A. It will be as a result of the deformation in AB, this section, as well as this section. So the deformation will be as a result of this side and that side. That is what will cause the point C to be displaced. That is what will cause the point C to be displaced. So having stated that, let us now put the deformation, because the question says that we should calculate the displacement of point C with regards to point A, which means that we are starting from point A. We are taking point A as our focus. So from there, we can say that II deflection at that side should be equal to, we said that it should be as a result of AB and BC. So from there, we can say that deflection of point A will be equal to 1.696 times 10 exponent -5 plus the deflection of BC, which is 2.89 5 times 10 to the power -5. And from there, the deflation of point C is going to be 4.591 times 10 to the power -5 inch. All these deformations are in inch. They are in inches. Don't forget about that. All these deformations are in inches. And the last one, we are asked to calculate the deformation of point D with respect to A. Point D here with respect to this displacement of point D with respect to A. So it means that it will be as a result of AB, BC, and CD. And so in the last question, we need to put all the three deformations together. The deformation of D with respect to A is going to be AB, deformation in AB, plus deformation in BC, plus deformation in CD. And when we put all the deformations together, then our answer is going to be 1.613 times 10 to the power -5 inch. And we are done solving the question. That was quite easy. And I hope everybody was able to follow us on this. Once again, we want to appreciate you for keeping in touch with us up to this point and always making it a point to join us in our sessions. We truly appreciate that. And if you have not subscribed, we kindly ask you to subscribe. You like, you share, you comment. And if there's anything you don't understand, you can also let us know. We'll be glad to assist you in that regard. Once again, thank you for watching and thank you for staying with us. Bye-bye. See you in our next video.